I'm going to talk about the Large Synoptic Survey Telescope. So as the announcement for this talk described, this telescope has now been named the highest priority for new U.S. ground-based observatories. And so typically that means it's going to get money and it's going to be built. Okay? And so this telescope is a survey telescope, which I'll describe in a minute. And so it's a super instrument. Let's see a little bit of that tonight. What I want to point out is the talk that I'm going to give is it's the result of a couple of years' work that included 5 Florida Tech undergraduates and 1 undergraduate near NASA in Alabama, where I was located prior to coming here. This guy here, Julius Allison. So the others, Chris Cullerton, Mohammed Furkan, Kerry Hoadley, Paul Regency, and Hakeem Wells, are all Florida Tech students. So there's a lot of undergraduate work present in this talk. All right. So LSST is the latest in a series of 3 survey telescopes, 3 ground-based survey telescopes. The first one was the Palomar telescope, which someone got the idea. I think Hubble was involved somehow, right? Let's take an image of every location on the available sky and see what we get. So they use these 14-inch square photographic plates. Now, if you want to make scientific measurements, you need to know, for example, how much energy you receive from an object. You might need to know the color of the object. So the Palomar survey was somewhat limited in that they only had images in 2 colors and that the images were on photographic emulsion. And the response of photographic emulsion to light is complex. It's very complex as compared to a digital imager. The light has a nonlinear response, or rather the film has a nonlinear response to light. Around 2000, the year 2000, the Sloan Digital Sky Survey came online, and it is exactly that. It's digital. And not only is it digital, which makes the data much easier to analyze and understand, but it took data in 5 different colors, 5 different photometric bands, which allowed a great deal more science. Now, both of these surveys imaged the entire sky once over the course of 5 to 7 years, say. All right? So LSST is the new telescope, and what it's going to do, first of all, let's talk about the sizes. This guy was the Palomar telescope was just a bit over 1 meter in size. The Sloan Digital Sky Survey telescope is about 2 meters, 2.5 meters, and LSST is an 8.5 meter telescope, 8.5 meter diameter. And so because of its design, which I'll show in a minute, it's a wide field telescope, so it will actually image the entire sky every 3 days. And it'll do that for 10 years. So now what we're going to have is a movie of the entire night sky that's visible from its location. That's 10 years long, which is pretty revolutionary. So these digital sky surveys are very powerful because with this one survey, you get millions upon millions of objects. So for example, we have a solar system that we live in, and it has this complex structure of different families of objects. You have the terrestrial planets in the interior. Then you have the asteroid belt. Then you have the Jovian planets. Then you have the Plutinos or the Kuiper belt objects. Then perhaps the Oort cloud. So how did it get to be this way is one question we may ask. How did it form? And so the Sloan Digital Sky Survey, for example, took the pictures of the colors of asteroids and found, well, look at the asteroids. If you look at their colors and their distributions, you see that they're in well-defined orbits, right? On the x-axis is the distance from the sun, and the y-axis is the distance from the plane of the solar system. And you can relate their colors to their composition, and you can relate their compositions to their ages. Which ones are from bodies that became differentiated due to melting, which of them are more primordial bodies. And what we see is the outer objects are more primordial. They're the carbonaceous chondrites, for example. So solar system formation can be addressed. The Hubble Space Telescope took this very famous image here, which is the Hubble Deep Field. And from this image, one conclusion that you may draw is that we live in a universe of galaxies. This is a tiny pinpoint on the sky, and as far back as you can see, there's just wave after wave after wave after galaxies. There's, I think, around 2,000 galaxies in this tiny region of the sky, which if we extrapolate it to the entire visible universe, comes out to something like over 100 billion galaxies in the entire visible universe. But with Sloan, you can use the colors to map out the the distances to these galaxies. And so here now we have a map of the galaxies of the universe that have been mapped by Sloan. And what you see is that it has limited locations on the sky that it views, these slices of the universe. And you can go out farther and farther. You can see regular galaxies, you can see the red galaxies, and finally you can see the quasars. And so this mapping out of the universe tells us a lot about how the universe formed, how it may evolve in the future, and allows us to address some of the current problems today, such as what is the nature of the dark energy that's accelerating the universe, and what's the nature of the dark matter, for example, that is in the universe and is associated with its galaxies. Very cool, right? Yeah. We're still going out. So when you look at an image like this that's cosmological, when you go farther in distance, of course you're going farther back in time, right? So we're going from the nearby, near our time universe out to the point that we can see the farthest in the universe, which is what we call the surface of last scatter, which is represented by the cosmic microwave background radiation at a redshift Z of about 1100. And so that's what we see here. And I think this was put together by the WMAP team at Princeton. So here's our galactic structure in general. We have a central bulge, we have a disk of gas and stars and dust, and we have the halo, which is a different population of stars, which has a different composition chemically from the stars in the disk, and the bulge also. And inside the globular clusters are, inside the halo are these globular clusters. Now, we're more interested in a detailed map. If we have a detailed map of our galaxy, then we can say something about galaxy formation. And it turns out that if you understand galaxy formation well, then that also informs universe formation. So this is one of the very important problems in astronomy today. Now, there is a detailed map of the galaxy, but some may question its accuracy. This is from Star Trek, people. I don't know. So just in case you're out in your starship and you want to know where to find the Bajoran wormhole, there you go. So here is the, in order to make this map, there's different techniques that you can use, and the technique that we're using is to use a type of pulsating star. All right, and so this pulsating star requires time-resolved observations. So here is the observations, the latest data from Sloan. My collaborating in this project is this guy named Branimir Cesar, and so he mapped out this one region here using the data from what's called Stripe 82 in the Sloan Digital Sky Survey. And what you see here, that loopy thing is the Sagittarius stream, and what you see is a new stellar overdensity that he discovered. And so these models of the formation of the galaxy, the prevailing model predicts that our galaxy should be surrounded by hundreds of satellite galaxies. And not only that, many of these galaxies, when they come near enough to the Milky Way, within our tidal radius, they should be tidally pulled apart and form streams just like this. And we found very few of these streams. So in this picture, you see the Sagittarius stream there, and there's another one that has to do with those red dots there, the Monoceros stream. But there's very few of these that are identified. So this is an important problem in galaxy formation, which is called the missing satellites problem. So that's what we hope to address with this research that we're doing. So LSST, what we just saw Sloan do was amazing, but LSST is going to see objects that are 100 times fainter, and is going to enable the time domain with these repeated observations. So every object will have perhaps 1,000 observations over the 10 years. So here is our best understanding of the makeup of our universe based on many different observations. And we also have a model of the evolution of the universe. And as I said before, understanding how our galaxy formed, which can be done by mapping out the galactic halo in part, will inform this map to see if we're actually correct, right? So if we truly understand something, then we can create a simulation. We can create a model, and we can test that model against what we really observe. And if we find that what we observe does not fit the model, then the model is incorrect. And today, there are different competing models for everything you can think of. Solar system formation and evolution, galaxy formation and evolution, and the formation and evolution of the universe. So we hope to test these, and of course there is some data that exists, but here's a simulation of a galaxy forming in isolation, roughly. And the thing that you'll see is that smaller structures accrete, they collide, and you end up with these tidal streams, and you saw that thing get stretched out there. And so we can test these theories. Here is what happens when a galaxy forms, and there's a violent history of mergers in the galaxy's environment. So many smaller galaxies form first, and then they collide with each other and build up a much larger galaxy. So we can look at a galaxy like the Milky Way, which is in a pore cluster, what we call the local group, and we can compare the observations of the Milky Way to simulations like this to see whether or not we know what we're doing. So here's an actual image of a halo model, accretion model, and you see many of these different streams that exist. And so we want to test, are these models correct? And not only do they describe a particular morphology, that you have these streams that are stretched out everywhere, they also make predictions about the chemical composition of the galaxy. Our galaxy, I called it the disk, but there's actually a thin disk and a thick disk, right? I described the halo. There's actually an inner halo and an outer halo. And these things accrete at different times, and in cosmology and astronomy, time means a difference in chemical composition, right? The very early universe had a very simple chemical composition, and as new generations of stars are born, they cook up heavy elements in their cores. Supernovae create even heavier elements, and when stars die, they eject a lot of their mass back out into interstellar space, and so that ejected mass is chemically enriched with heavy elements as compared to the previous generation of stars. And so you can test the chemical composition predictions against what we observe as well. So for example, here our inner halo should be about 9 billion years old, and it should be metal rich because of many supernovae going off in our galaxy. And then we have an accreted outer halo that our galaxy accreted later through gravity that would be more metal poor. There would have been fewer stars in this region, so it would be less enriched with heavy elements. So what do we want to do? We want to map out the halo pretty much and measure the chemical composition of it. And then we can compare that with simulations. So to do this, we use a particular type of star. It's an RR Lyrae. So here's a globular cluster, which is a halo object. And you can see these stars that are pulsating, getting brighter and dimmer. These are RR Lyrae stars. So it turns out that the most difficult and the most important problem in astronomy is that of measuring distance. And there are types of stars that allow us to measure distances with a reasonable degree of accuracy. How do they work? Well, these pulsating stars like RR Lyrae and Cepheid variables, their pulsation rate is related to their brightness. So all I have to do is measure that this guy is an RR Lyrae star. I know how bright it is intrinsically. If I know how bright it is intrinsically, I can compare that to how bright it appears, and that tells me the distance to the star. So the next question is, can I identify RR Lyrae stars? Well, if you look at the pattern by which they brighten and fade, what we call a light curve, this is the brightness as a function of time. On this scale, or what we call magnitudes, the higher the magnitude, the dimmer the star is. So as it gets dimmer and brighter, it undergoes the same pattern over and over and over. So by looking at that pattern, we can identify this star is an RR Lyrae star. And once I know that, then I can calibrate its brightness. And the calibration is within about 5%, which is very good in astronomy. If you want to map out the halo, which is very, very far away, right? It extends very far, or the local group, which is, our nearest large galaxy is 2 million light years away, then you need to be able to see these things very far away. So these guys are very bright. So they're much bigger than the sun, so they're very bright, and they're variable, which allows us to identify them. And not only that, they're numerous. They are smaller than the sun in mass, and with stars, the smaller you go, the more of you there are, right? So there are very few large stars and many more small mass stars. So these types of stars are more numerous than stars like the sun. And not only that, because they are small mass, they last for a long time. So if we're looking to map out the history of the Milky Way galaxy, then what we want to look at are fossils. So these stars sort of serve as the fossil remnants of the ancient galaxies that accreted to form the Milky Way galaxy. They come in two types. There's the RRAB type, which is here. And so this gives you the period of their pulsation, which is less than a day, which is good because over one night we can measure them actually changing their brightness. Then there are type RRC. And these guys have very short periods and their amplitude of variation is not very much. Okay? And the difference in this type and this type is in the way they pulsate. These stars are radially pulsating. They're getting bigger and smaller, right? Hotter and cooler, brighter and dimmer. What I said didn't match up exactly, by the way. And here are the differences in their light curves. The RRAB have this more complex structure, and the RRCs are more sinusoidal in shape. And so the map that you saw earlier from Branimir Cesar paper, the stars that we see here are the actual RR Lyrae stars that he used when he made his map. Okay? And so what we did is we selected a subset of those stars, and we took their light curves, and we're using them in our simulation to determine how well LSST will be able to do this job. So another interesting thing is that the stars' light curves look different if you look at them in different colors. All right? They have the timing is the same, but the shape is slightly different. And that gives us information about the stars. So here is LSST. In one image, it's going to see 10 square degrees. How much is that? Well, the moon and the sun are about a half degree on the side. So imagine you take 20 moons across, right? So that's 10 degrees in that direction. But it's really 3 degrees by 3 degrees, right? Square root of 10, right? 3 degrees by 3 degrees. So that's like 6 full moons on the side. Its primary observation mode is it's going to go to a field. It's going to take 2 back-to-back 15-second exposures. It's going to go away and observe somewhere else. 30 minutes later, it's going to come back and do that again. Those 2 15-second back-to-back exposures. Every night, it's going to download 30 terabytes of data. All right? Compare that to the Sloan Digital Sky Survey, which produces about 200 gigabytes per night. It's going to be a 10-year survey, and the very night the data is taken, it goes into a database that's publicly available to the entire world. All right? Now, the thing is that when you have data of this magnitude, you do not have the ability to sit there and look at every image. So the key here is to build software to perform the automated analysis of this data. And this problem of dealing with big data is a problem in many different fields. So one of the early contributors that's private, one of the early private contributors to the LSST has been Google, believe it or not. So it's going to be located in Chile, near the town of La Serena. And here it is near the site of the Gemini telescope, which is a wide field-ish telescope. Here is the design of LSST. It's a 3-mirror design. So it has a primary mirror that's 8.4 meters, but the effective size of it, the collecting area, is equivalent to just over a 6-meter telescope, about 6.6 meters. Light comes in, strikes the primary, goes to a secondary. The inside of the primary has a different shape and actually forms a tertiary mirror, and then the light goes there to the focal plane where the images are taken. And there's the ray tracing diagram and the point spread functions for those of you who are technical enough to appreciate such a thing. So here's the size of the camera. It should be the world's largest digital camera ever built. You see the filters, the green, red, yellow circles are there that are mounted inside. That's an image of the focal plane. Very expensive. It has 6 filters, which defines the photometric bands, the colors in which images are taken, which allow you to perform the science. Here it is compared to the Gemini telescope. Much bigger field of view. And so the LSST has 4 main science themes. One, to map out the nature of the dark energy and dark matter in the universe. The second, to make a solar system map. The third, to look at the transient universe. There's a variety of, that should be time, phenomena that occur at different time scales. And so this telescope will open up the time domain for a major region of the sky, 20,000 square degrees. Remember that map from Sloan Digital Sky Survey where there was data? That was about 300 square degrees, right? LSST will look at 20,000 square degrees. And the Milky Way map, which is what we're going to talk about here. You see that it says that it'll map out stars out to about 400 kiloparsecs. When it was designed, that was the belief to how far we'd be able to observe structure. However, after this study, we find that that number has been radically revised. So here's our simulation. What did we do? So we selected, so these regions that LSST will observe are predefined. All right, so the main observing sequence where it takes two back-to-back 15 seconds and then comes back 30 minutes later, where it tiles the entire sky, those are called the universal cadence fields, and they're designated as blue. Now, we don't want to miss any regions of the sky, so these universal cadence fields overlap with each other a little bit, right? It's like mowing a lawn, right? Yeah. So what happens is that these overlap regions are observed more often than the universal cadence fields are observed, right? At least twice as often. And so we also have studies that are designated for the plane of the Milky Way galaxy, which are yellow, and for mapping out objects in the solar system, which are shaded pink. And then we have these 7 fields, which are designated deep drilling fields. In astronomy, you can play a nice trick. What you can do is if you take repeated images of the same location on the sky, you can add them together. And so you can get a really deep image. So if I take repeated 15-second observations over and over and over again, right, if they add up to, say, 3 months, then that image is the equivalent of just leaving my telescope open and looking at that one region of the sky for 3 months and collecting light and seeing very, very deep. So these are called deep drilling fields. And the way that the deep drilling fields work is that you go to a field and for 10 minutes, you just take back-to-back 15-second exposures, right? So you get 40 images in a 10-minute time period every night. All right? So what we did is we placed stars. We took our group of 40 RR Lyrae stars, and we placed all 40 of them in each of 1,007 locations. All right? And then we wanted to place them at different distances. All right? How far away, at what distance does LSST crap out? It can't see anything else, right? That's the question. So we designate distances by setting their magnitudes. 18 is a bright magnitude. That's about 30 kiloparsecs, right? Which is roughly parsec is about what? 3 light years. 3 times 30 is what? 90? Yep. Okay. Out to magnitude 27, which is about 2 million parsecs. All right, so 30 kiloparsecs, so that's 100,000 light years to about 2 million. And so at half magnitude increments. And so then we wanted to see, and so then we imaged each one in 6 filters, right? So we did the survey in each filter. And then we also looked at the evolution of information. So what do we know after 1 year of data? What do we know after 2 years of data? What do we know after 3 years of data? So when you multiply all that up, we actually produced over 36 million different light curves. And that was the easy part. So now we have a simulation of the Large Synoptic Survey Telescope. And this simulation is based on the instrument itself and the site that is going to be observing from. So when I place a star on the sky, I start my simulation going, and on the simulation it's going to say, okay, today is May 1st, 2016. All right? So typically, what's the weather like at this location on May 1st, 2016? All right? Where is the moon on this date? What is its phase? And that determines how well you can observe the object, right? If you have a clear night, clear weather, and no moon, then you're able to get a very high precision measurement. But if you have the moon visible, zodiacal light, weather's not too good, right? Then you have a very low precision measurement. Your error bars get very big. So we simulated 10-year observations. So here are universal cadence after 1 year of data and deep drilling fields after 1 year of data. So what you'll notice is really obvious in the deep drilling fields is that the data occurs in these stripes. So what's happening here? You have this star that's brightening and fading, say, on an average a half-day time period. And your telescope is going to look at it, boom, boom, at some phase, right? These 2 back-to-back 15-second images, right? You don't know where it's going to be in that, what we call the phase of the light curve, right? Between 0 and 1 as it brightens and fades over and over. And so we observe in seasons. For 6 months out of the year, a star over here in this part of the sky will be visible. Next 6 months is going to be hidden behind the sun. And so what we have to do is take all of this data and now put every data point in its proper location in its phase. right? So here I called it at brightness, so that goes in the bright location. And so what we see here are reconstructed light curves from data like this. So the first thing you have to do is you perform an analysis of the data to determine the periods that exist in the data, divide the data by that period, and then the fractional part of that tells you where it goes in its phase. Now, the deep drilling fields appear to have much more noise, and that just has to do with the fact that you observe much more often, so your probability of getting a bad night gets higher, right? So you have more bad nights with more bad data. It doesn't mean that the data is worse for the deep drilling fields. So these are reconstructed light curves. So now that we have those light curves, what are we going to do with them? What are we interested in? We need to know how far away this thing is, which we determine by measuring its brightness. We need to know its chemical composition. And it turns out that the shape of the light curve changes depending on the chemical composition of the star. So we can distinguish, if we take a map and we map out these stars based on their location, and then we color code them based on their chemical composition, then you can identify stars that were formed in the same environment, if that makes sense, right? And so the first thing you have to do is recover the period. Now, this is a science within itself, and the stars have a range of periods. Some vary their brightness on a scale of 0.2 days. Some vary their brightness on a scale closer to 1.2 days, for example. And so if you want to measure the period of the star, if you're incorrect, remember what we're doing. We divide every date by the period of the star and then take the fractional part. So let's say this thing is brightening and fading over and over again, right? And I have all the data. And I wish to say, okay, I'm going to put all of the data into one phase. So I have to so as it begins cycle 2, I take cycle 2 and I shift it over here. Now I take cycle 3 and I shift it over there, right? And I do that. If I'm off by a little bit, then what's going to happen is that there's going to be a shift in the light curve. The data points aren't going to fall exactly where they're supposed to, because the one that's supposed to be here is going to end up here now, right? So we ask ourselves, what's the maximum shift that we're allowed in order to see a nice shaped light curve, right? So that's that delta phi max. Now, those stars that have shorter periods will go through more oscillations in that 10-year period, right? So that error is going to be bigger for those stars because they went through more oscillations. Because the more you shift this thing over, right, the more that little offset builds up. So that's what that n is, the number of oscillations. And then sigma sub p is the error in recovering the period. And so we can create a criterion which says that the error in recovering the period must be less than some value in order to get a well-shaped light curve. And then we can ask ourselves, how often do we actually recover periods to within that criterion? And so here is a plot that shows you for stars that have a short period, for stars that have a long period, what is the criterion with which you must recover the period in order to get a nicely folded light curve? So it's something like 10 to the minus 5 on average. So let's say for 10 years of data, if my star has a period of half a day, then in order to have a well-recovered light curve, then I have to recover that period to within 0.22 seconds, is what that criterion requires. That's pretty tight, 0.22 seconds, right? A fifth of a second. So what we have here, all right, it's getting a little complex. I'm sorry. So what we have here is, as a function of magnitude, which is how far away the star is, it's really how bright it is, right? With bigger magnitudes means a dimmer star, and we can relate that to its distance. How well do we recover those periods, right? And so here are some interesting distances. 30 kiloparsecs is where our current models of the distribution of stars in the halo extend to. That's about 18. The Milky Way tidal radius, within which stars should become tidally disrupted, is about 300 kiloparsecs. That occurs at r equals 23. We currently don't have any observations, or not many observations at that distance. And M31, the Andromeda galaxy, occurs at an r of about 25. All right. Now, when we look at the galaxies and we compare the models, certain things are confusing. For example, another member of our local group is the galaxy M33. Although the Milky Way galaxy has a halo, of extended stars. The Andromeda Galaxy has a halo of extended stars. There's evidence that the large and small clouds of Magellan have these halos. M33 has not been observed to have a halo yet, right? So it would be good to observe a galaxy like M33, which extends out to an R of about 25.5. So can we reach that? And so these are the median magnitudes reached after a certain survey length. So we see here in the deep drilling fields, we can get out to about 25.5 for the median value. So here we look at as a function of amplitude, how well at what magnitude do we recover the period for 90% of the stars? The red dots are the RRAB stars, which have a narrow light curve shape. And the blue dots are the RR type C, which have a broader, more sinusoidal shape. And what we see is that the red dots are below the blue dots, right? And that means that we can see the RRABs out to greater distances, that we can recover the periods of RRABs out to greater distances than we can recover the periods of RRCs. So here's how that works. Suppose I want to know the period of a pulsation. If this thing is like what we call a delta function, a very sharp thing, right, then you should be able to determine that period very, very precisely, correct? Except for the fact that you might miss it, right? So there's a trade-off. You don't want it to be narrow, but not too narrow, right? And so the RRABs are narrow, but not too narrow, and the RRCs are wide enough that you can see the difference. And also, as a period of pulsation gets bigger, then you can recover their periods out to greater distances, right? Because their distances are set at their mean magnitude, which is sort of the middle of their brightness variation. So as they go farther and farther away, you don't catch them in their dim parts of their cycle. You only catch them in the bright parts. You can still get the period of pulsation, but you may not be able to get the shape very well. This must be a doozy. Okay, so here we have the surfaces of period recovery. All right, so what does this mean? We ask ourselves, of all the stars that we put on the sky in this simulation, what percentage of them, for what percentage do we recover the periods? Okay, and so we do it as a function of survey length and as a function of their distance away from us. So here I've taken some slices after 1 year of data, 2 years of data, 5 years of data, 10 years of data. The black line, the solid lines are for all stars, and the dashed lines are for type RRAB stars. And what we see here is that the limiting survey from the limiting magnitudes for, say, the Sloan goes out to 21.5, 22, 22nd magnitude. And we see that in the universal cadence, which is the majority of our stars, we get 90% of stars out to 23, which is where the Milky Way tidal radius is, right? So after 10 years, we're going to really be able to map out the data, map out the halo really well. Now, another interesting thing to note is that the deep drilling fields, 2 years of deep drilling data is equivalent to about 5 years of universal cadence data. So that's an interesting thing that I'll get back to in a minute. If we look at the overlap fields, it's slightly better than the universal cadence. If we go to the Milky Way fields and the solar system fields, then we see that the recovery is not as good. But those were not designed for studying the halo. They were the solar system fields were designed for looking at moving objects, and the Milky Way fields were designed for doing tests in the plane of the Milky Way, not in the halo. So here is an interesting thing that we notice. If you look at 2 years of Milky Way data, and you compare that to 1 year of universal cadence data, you see that the Milky Way data is much better. Something's very odd here, because a single Milky Way field only gets about 30 observations over the entire survey, whereas the universal cadence data will have about 1,000 points each. Okay, so what's the problem? The problem is that the algorithm that decided what field you're going to look at, the way it worked was, if a field was near completion, so say this universal cadence field here, I know that it's supposed to have a total of 1,000 fields. Once it gets up to 800, 900, then I give that field higher priority since it's near completion. Because the Milky Way fields have such a low number of observations required once you begin their near completion. So the Milky Way fields were all observed in the first 5 years of the survey, and then there's no improvement after that, right? It was actually after 3 years. So in this simulation, we actually discovered an error in the algorithm that was used to design how LSST is going to work. I guess I should mention, I don't know if it shows up later, but we also did the same thing with the deep drilling fields. Remember how I told you that 2 years of deep drilling data is equal to 5 years of universal cadence data? Okay, that seems to say, hey, the deep drilling fields are more efficient. Well, actually, they're not. And the reason why they're not is because every night you take 40 observations in deep drilling fields, and every night you take 4 observations in universal cadence. So that's 10 to 1. And so if you calculate how many observations you have in 5 years of deep drilling data compared to 5 years of universal cadence compared to 2 years of deep drilling, you have many multiples more observations in the deep drilling. But you don't recover the periods as well. Why is that? The reason why is because they're clustered together. So as this thing is, if you want to recover the period, you want your observations set kind of far apart in the phase. Does that make sense? So instead of doing 10 minutes of continuous observations, if you did 5 minutes of observations in deep drilling, left, 30 minutes later, did another 5 minutes, then your efficiency would go up. And so perhaps 1 year of deep drilling data would be equivalent to 5 years of universal cadence data. So that's another discovery that we made in this study that has impacted the actual operations of LSST. So what else do we want to do? So we want to measure the periods in order to make nice light curves. We also need to measure their chemical compositions. How can we do that? Well, remember I said that the shape of the light curve depends on its chemical composition. So every student in physics has to take classes in calculus and electronics and things like this, and they learn about Fourier decompositions. So what does this mean? If I take any function that's continuous and differentiable everywhere, then it can be expressed as a sum of sine or cosine functions. And so that sum looks like this. So it has an amplitude, is an important part, and it has a phase. So basically what I'm doing, and a frequency, I'm taking different sine functions and I'm giving them different amplitudes and I'm shifting them relative to each other and I'm giving them different widths, okay? And then I add them together and they can form a different shape. And it turns out that if you take the phase of the third term in the series and the phase of the first term in the series and you take that difference, we call that phi31, then the chemical composition of the star, the ratio of iron to hydrogen, actually scales with that quantity. Which is, okay, we'll accept it. We observe it's true, but interesting, right? So if we can perform a Fourier decomposition of our light curves, then we can measure metallicities. And so that's what we've done. So here I have, okay, this is a little complex, but basically we look at the recovered light curve and we compare the phi31 calculated from the input light curve to the phi31 calculated from the recovered light curve. And we call that delta phi31. And so if we recover delta phi31 to within 1 sigma of the delta phi31 that we get for the very brightest stars, then we say we've successfully recovered the shape. And so the dashed lines here show you how well we recover the shape as compared to the periods. And you see that they're very closely matched, right? So what this says is that if we're able to successfully get the period, then we should be able to get the light curve shape and the chemical composition. I'm going to skip that and that and that. And the other thing we do, another approach, is to do what we call template matching. When Branimir Cesar looked at his 600 or so RR Lyrae, or 500 that he had in his survey, he found that he could fit templates to them. So he could find these set of basis shapes that all of the stars could be fit by manipulating these basis shapes. So for the RRABs, he found about 20 in each color, right? So no matter, he had 500 stars, 3/4 of which were RRABs, so let's call it 400, and those 400, or let's say 375, those 375 stars are well represented by only 20 template shapes. for the RRCs, he found that the 125 that he had were well represented by only 2 different template shapes. So we can template fit these light curves because in the beginning of the survey, we're going to have very few data points. And if you have very few data points, then you cannot do a good Fourier decomposition. And also, because you already know the shapes of these things, and all you want to do is shift it up or down, stretch it, shift it left or right, then if you want to recover the magnitudes very well, right, how bright they are, then using this template fitting allows you to do that. Because how do you define how bright this thing is if it's changing its brightness constantly? Right? How do you do that? The way you do it is you relate it to the energy that's produced in the interior of the star. So if you convert these magnitudes to fluxes, which is the actual emergent energy from the star, and then you integrate all that flux, then what you get is a magnitude that represents how bright that star would be if it were not pulsating. Right? So if you have very few data points, it's very difficult to do that. But if you have a template that you can fit to those very few data points, then you can perform that operation on the template itself, right? And you can recover the brightnesses to a very high precision. And so what we see here is after 9 years of data for a star that's very far away, magnitude 24.5, and here we have a bright star after 1 year, magnitude 22. And so we see here that the template matching results in the out years do not recover shapes as well as the Fourier thing did, okay? But it did recover brightnesses much better. This is also, we want to type them. How many are RRAB? How many are type RRC? So that's what these two represent. The left side is type RRAB and the right side is type RRC in the different fields. How well do we recover their actual types, which is important for people who study the stars themselves. So here is a plot of the error in returning the flux, the error in returning the brightness of the star based on the Fourier technique and the template fitting technique. All right? And so what we see is these things stay flat until we get out beyond magnitude 23.5. So what that says is that the median error is very small until we get out there. But what percentage do we recover? So we see here for the deep drilling fields, we pretty much get the brightnesses for 100% of the stars very early in the survey, although there are a few data points. But when we go to the universal cadence, we see that the template fitting recovers the brightnesses just as well for those guys as it did for the deep drilling, but the Fourier fitting does not. So these two analysis techniques in the RR Lyrae community is kind of an argument, right? Do we do the template fitting approach or do we do the Fourier decomposition approach? And the answer is yes. Right? They do different things. So in conclusion, we'll be able to see 97.5% of stars out to those magnitudes in those fields, 90% of stars to those magnitudes in those fields, and 50% of stars to those magnitudes in all of these fields here. So this is all the way beyond the Andromeda galaxy. So 25.5 takes us all the way to M33, which is 2 megaparsecs away. So we'll be able to map out, if you remember, the LSST science book said that we'll be able to see these things out to 400 kiloparsecs, right? We'll be able to see them much, much, much farther than that. And so what we've done here is we've been able to, the most important thing we've done is in doing this survey and doing this analysis. By the way, recovering the periods, we had a 1,000-node cluster at the University of Washington that went about doing that analysis, and it took it about a month to run through all the 36 million light curves, right? So when LSST actually comes online, those who are going to be able to analyze the data are those who already have the software infrastructure in place. So perhaps for me and my research group, the most important thing is that we have put the research infrastructure in place to do this science now, right? And so my students who are undergraduates and are graduating now, one is already in graduate school, by the time they're ready to finish graduate school, they'll already be ready to do this science by the time LSST comes online. We made 2 strong contributions to LSST operations, and otherwise it's all good. So thank you.